Hey, morning, everyone. Appreciate you coming. We figure you're either really interested in this topic, here to support us, or you are lost from last night. So thank you for coming. So this is resolution scaling, frame generation, GPUs, and other Bramble pits. We're going to go through an overview, a little bit about us, a little bit about our studio and where it fits into the ecosystem and why we do this kind of thing. We're going to do some of the concepts and technologies at a general level for those people who aren't familiar with resolution scaling and frame generation. We're going to do some very specific case studies and some examples within those case studies that we've done recently, some very, very recently that we'll talk about today. We'll talk about some of the challenges and considerations as you look at this tech, both at the front of your pipeline, but also after you've finished your game and you're adding it after the fact. We'll hit some of those asset changes or impacts and product decisions. And then we will spend a little bit of time talking about how important it is to take care of our partners and how we can elevate each other and do more with the technology. So real quick, welcome and introductions. My name is Adam Creighton. I'm the founder and studio head for Enduring Games. I got into video games by way of voice acting, transitioned to game engines and middleware. I do Enduring Games now and have done some interesting things in between. Kevin?
Hey. Nice to meet you all. I'm Kevin Napoli. Been doing graphics and rendering for quite a bit now. Started with Arcane and then got introduced to Adam. Greatest decision yet?
Greatest decision. That's a high bar. All right, so let's talk a little bit about Enduring Games and why we're doing this kind of thing. So in relation to Epic, we do quite a bit with Epic. There are several people in here. You've probably seen us answer some of your UDN tickets. We do UDN support on behalf of Epic Games. We are a licensee. We're a high-end co-development studio, and we also do ports and remasters. So we have a bunch of avenues where we intersect with the Epic Games team, and we get to see quite a bit about how they are able to help developers, how we're able to plug into their technology stack, and how we can leverage it in unique ways. From a studio focus perspective, we hit broad areas as a co-development studio. The lion's share of our work is services partner work, where we do, alongside a team, we help games get made. Our success criteria is we generally come into a game and do something that wouldn't happen unless our team is involved. And we are top to bottom. We are engineering, tech art, design, product, QA. So we hit all of the areas that are needed as we do development for our partners. We do digital distribution, which are really just targets of opportunity for smaller developers that have a title that we would like to move to a platform, but they don't have the experience, expertise, or relationship. So we help them with that, kind of publishing without the marketing side. And then we do original intellectual property, which is not just games. We do a lot of technology development, including some of the things we do with scalable resolution and frame generation. So I talked about what we are in relation to Epic Games. Even outside of that, we've done quite a few titles as Enduring Games, and our staff has done close to 200 titles. I maintain a very detailed list of all of our current staff, the projects they've worked on, the genres, the technology stacks, the pipelines, because it lets us adapt very quickly. And one of the biggest things that I think the game industry benefits from is context. And so I really like to know what people have worked on, what they've liked working on, what they want to work on again, and solve problems that have been solved before, not reinvent the wheel. So a couple of things to keep in mind as we do this. So we're really just looking at the solutions that integrate into the render pipeline. And we're going to do direct experience with some case studies to make it more grounded, more real for what we're talking about. And we've intentionally captured some of the videos we're going to show at a lower resolution than what we're showing on the screen so that you can see a little more of the artifacting. It's a little more apparent as we do some A/B comparisons. Resolution scaling and frame generation are a very evolving technology. They're moving super, super fast. We enjoy being on the front of that, but there's some trade-offs, especially when you look at like hardware or hardware agnostic implementations. And it is not a one-size-fits-all solution. You can really look at how you can mix and match different resolution scaling, frame generation, and related technologies, and we'll give some examples of that. There are getting to be a lot of solutions, right? You've got TSR, DLSS, FSR, PSSR, XeSS. There's a lot of solutions, and we tend to look at all of them because we really want to understand where the landscape is shifting, and there are benefits outside of just frame smoothing and other opportunities with the tech. The challenges you will see as you implement this for your game are not always related to the IHV or to a single IHV, an independent hardware vendor. So sometimes there are conflicts with the implementations. Sometimes it's game side, but it'll look like it's a rendering artifact related to resolution scaling or frame generation. So working with game teams intimately and really understanding where the problems might be is the opportunity there. A lot of product decisions as you're implementing resolution scaling and frame generation. Assets are going to change, especially if you implement either or both of the technology stacks after a game is largely finished or getting ready to ship. There are brand and UX considerations that you need to think about as you take care of each of the independent hardware vendors. And one of the big ones, the benefit of frame generation is really frame smoothing. It is not free doubling or getting increased frame rate just by integrating it. And it's pretty important that and we're going to talk about that in a little more detail. So I'll wait on that one. It's magical, but it's not magical. So it's moving fast. It's really cool, but it's not a silver bullet that's going to solve all of your stuff. And it's going to be very case by case specific. Testing is really important. It's extremely important, and it's going to be different for each of your games. So talking about the testing side of things, so we do a lot with all of the different technologies. And so as part of that, we like to make sure we're doing performance captures, A/B comparisons, timings, so we understand how the different technologies are working on different hardware stacks, how they compare to each other, what challenges we might see from an artifacting perspective to timings. And we capture several different parts of this in our test matrices, including whether frame generation is on or off, VSync on or off, refresh rate, build IDs, build configs, the operating system, CPU, GPU, the RAM, which independent hardware vendor we're particularly looking at, or combination of hardware vendors, quality modes, all of that. And we measure that, things that you would expect, CPU draw time, GPU time, frame rate, the memory, virtual memory. We just try to hit all of it. But in practicality, what it looks like is something like this, right? We have ginormous matrices. It's my eye chart. But we do these big matrices that we can slice and dice multiple ways, so we can look at how the different tech stacks up to each other. And it's not a faster, slower necessarily. Because we tend to be in the middle and work with all of the different partners, one of the things that this allows us to do is be an independent provider that can say, okay, this is how things stack up, and without us crossing any lines or breaking any firewalls, we can show how your stuff does on this different hardware that maybe you don't have a chance to look at. So that works out pretty well for us and for our independent hardware vendors. So let's go real quick through an overview of the general technologies, and then we'll go into some of the implementation and specific. Kevin?
Thanks, Adam. Well, if that testing grid didn't scare you, you're still here. I'm going to take that as a win. So what is resolution scaling? So we're going to introduce some of the concepts, even if it's something you've already worked with, just as a recap. So we're trying to render to a smaller target and then upscale it to display resolution so that you don't have to do as much of the work that you would have otherwise done. And there's a lot of solutions out there right now. And the way we sort of differentiate between them is what is hardware assisted versus agnostic. NVIDIA's DLSS relies on the tensor cores within Ampere chips to actually do the work with AI inference. And Intel's XeSS is similar in that they use the DP4A and the XMX chipset on their Intel cards to actually support resolution scaling to make that faster on Intel hardware. The special case with Intel is that they also have a non-agnostic approach that uses shaders instead as a fallback for when the customer doesn't have Intel hardware. For agnostic ways, there's also two things that EPIC supports already, temporal anti-aliasing upsampling, which is TAAU, and temporal super resolution. Both of them come packaged in with Unreal, TSR specifically with Unreal 5. And TSR is also enabled by default. So if you just start a project, you get TSR out of the box. AMD did Fidelity Effects Super Resolution, FSR. They're a software-based approach using shaders, and they have other things than just super resolution scaling as well, which we'll cover in this talk. So frame generation. So Adam mentioned briefly, frame generation is not necessarily doubling your frame rate, right? The best case scenario you're going to get is you're trying to smooth the experience for the player, which means you're adding more frames, just it's not going to be actual rendered frames. You're interpolating or using some sort of inference to generate a frame. So if there are artifacts in those interpolated frames, you will actually see the artifacts in a better light depending on the refresh rate, which is why we do a lot of refresh rate testing. And same way, there's hardware assisted and hardware agnostic. DLSS uses machine learning to generate the frames. FSR uses software and shaders to interpolate the frame. So a little bit about implementation. For TSR, it's built into UE5. We'll go over a little more in the next slide, but other IHV solutions actually provide Unreal Engine plugins as well. So part of what you need to discuss or decide on is where you're going to end up with your engine upgrades. And part of when you integrate your plugin also comes in with that, because every version of the engine gets its own Unreal Engine plugin, and it may or may not just scale and just work. Frame generation, one thing to keep in mind is it's not something you can test in Pi, in editor. We did test standalone game, but the best test case for your game will always be cooked and standalone with cooked platforms. And please test on device. That's going to be the biggest case here. Frame generation is is adding a lot of load to your GPU as well. So always testing on device is going to be a pretty big comparison. And one thing that current gen of frame gen solutions have started doing is decoupling both the resolution scaling. So we did discuss that resolution scaling works well with frame generation, but there are alternatives where you can decouple it, and we'll be talking about those combinations. Part of what this allows is you can pick the best combination that works for you. So, there might be resolution scaling from one vendor, and you might like the frame generation from another vendor. It really depends on the product decisions and the product goals and how it looks in the game. So, let's do TSR. It's built into UE5, and like I said, if you create a new project, TSR is the default. So because of that, Epic is doing a lot of work into optimizing TSR as well. TAA is the old approach in UE4, and TAAU is an extension of that to actually do the upsampling. And TSR tends to be more expensive because it's doing better visual fidelity on things that are moving, and it does support async compute. So the reason I have the asterisks out there is NVIDIA hardware with Unreal, they only enabled async compute by default, starting from 5.3, specifically on the Ampere-based GPUs. So keep in mind on all kinds of GPU dependencies you may inject based on trying to support async compute versus not. As far as turning it on, it's controlled by the CVAR there. It's anti-aliasing method. The value of 4 is the value that TSR uses. And Epic built a really cool visualizer for actually helping debug artifacts. So one of the big things we will focus on today is artifacts and product decisions. So that's one of the ways you will debug it. And Epic has done a real good job on documenting the entirety of TSR and its passes and how things flow within the passes as well. And when you have other plugins integrated, and if you turn off the associated enable flags on those plugins, TSR becomes the fallback, and if anti-aliasing method is set to 4. A little bit about DLSS and frame generation from their side. They provide 2 plugins, DLSS and Streamline. So Streamline is the container for frame generation and reflex. Frame generation is the great thing about frame smoothing and doubling your frame rate. And reflex is trying to reduce the latency when you're actually doing that. one of the big things you'll encounter when you're doing frame gen on your game is input latency. And there's actually solutions right now that help reduce that input latency by reducing the system latency from render to display. Streamline hooks into the swap train creation. So it's not just a sort of plug and play from it doesn't just turn on and it just works. There is a little bit of engine edit that goes into it. But from an integration standpoint, like you get a DLL, that's the primary component for DLSS. So patching that DLL later, it can be minimal, depending on what you're trying to achieve with the patches later on. One thing that we've done a lot of work with is every code base we try to work with, we always try to wrap it with the macros with DLSS and with Streamline, so that it's easy to either change the plugin and not entirely change your code all the time. And like I said, underlying library is provided as a DLL, so it is a closed DLL, and maybe if you're getting patches from NVIDIA, that pretty much is the minimal patch you're going to get. So as far as support goes, resolution scaling needs RTX. It's machine learning, so all RTX cards are supported. Frame generation specifically requires 40 series and above. The good thing about the plugin is that they provide blueprint and function libraries to help you see if the support is there for the platform, and you can do your UI based on that. And all of these plugins actually require DX12 as well. A little actual official documentation on what's supported on what hardware, and let's do FSR. All right, so FSR is AMD's solution for resolution scaling and frame generation. It is an open source plugin that has wrappers for DX12 and Vulkan. The release, like I mentioned before, also has a UE plugin for the different versions. I think they have 5.1 through 4 right now. Starting with FSR 3.1, all of the fidelity effects code can be built into a DLL and just put into the UE plugin, which can later be patched separately if needed. It doesn't require hardware components like we were talking about. It is hardware agnostic, and it uses a software-based approach, and it can run on any hardware. There's asterisks there. The UE plugin provides 2 backends for FSR to work. So there's a RHI backend, which is platform agnostic, with a lot of asterisks there. And the native backend, which is the more optimized, more feature-rich version of the plugin. And when you're working with the RHI backend, to support more pacing, so one of the big things that comes with frame generation as a solution is you have to know how to pace your frames as well, because not all displays will be able to render at that additional frame rate, and doing the pacing weights and the pacing logic is going to become more key when you're dealing with this technology. So a little bit about the RHI layer. It is platform agnostic because FSR uses the Unreal RHI to actually drive all the command lists and the commands, and that goes into the platform you're dealing with. So whether that be DX12 or Vulkan, UE is making that abstraction. But when you're dealing with this, you're dealing with the platform as well. So shaders will actually require adjustments when you're trying to, depending on the console hardware and depending on our mobile hardware in this case. And because not all of the features are supported for console and more constrained platforms. In this case, you don't get support for async compute or async presentation. So async presentation is one of the things that you will need to achieve the pacing weights and the pacing logic I was talking about before. And in this case, it uses Unreal's frame pacing instead. And a little bit about that resync on case. When you're dealing with interpolated frames, you can have the RHI pacing mode control how your real frames are synchronized, essentially. And in this case, it basically puts the real frame on vsync versus the interpolated frame can have tears in between. A little bit about the native backend. Passes run without using the UERHI, which means it's running its own DX12 code or Vulkan code. In its abstraction, takes some context variables from Unreal and has added. The iteration workflow in this case is super fast because you don't even have to cook. You don't have to build the entirety of the engine. You're building the plugin by itself, which is a separate solution project now that everything is a DLL. There are no shader permutations injected here. It's all pre-baked into the DLL, and it's part of the separate solution build project, which means, which means there's no cook necessary even when you change shaders. And a little bit about the pacing frames. This is actually from AMD's integration docs, and essentially the part of what we have to deal with is current technology supports a lot of display resolutions, and with it comes variable refresh rate as well. The pacing logic they have in place helps quite a bit with the VRR support, and this actually enables users to use a vsync off approach as well when you're doing frame generation. And a lot of the frame generation passes actually can run on the async compute queue when you use the native backend because you're no longer bound by Unreal's rules of using async compute or not. So this can potentially help on the thing on the hardware that doesn't necessarily isn't turning on async compute by default, even in the Unreal Engine. And, oh, spoiler alert, that's one of our backends running on the Xbox platform and shows how interpolation can actually run on the graphics queue or the compute pipe in parallel with the next frame that's coming up. And for support, this is AMD's recommended specs for things we want in terms of GPUs and vendors. A little bit about XeSS. So as I said, this is a approach that either does hardware assistant approach with Intel optimized hardware, and specifically using the Xe HPG architecture. And those are the Intel Arc GPUs. And if the Intel GPU is not available, then they will use a HLSL-based approach. And it tends to be, depending on what you're trying to do, you have different problems to solve on either case. And same way, Intel's library is provided as a lib file, which lives in the UE plugin, and it just plugs in and it works with the engine. All right, case studies.
Thanks. Appreciate that, Kevin. Okay, so we're going to go through some examples because we do very active development, so we wanted to make sure it wasn't too just high level, and we wanted to dig into it a little bit. And we're going to go through 3 projects: an internal project, Legend, that's internal to Enduring Games, and Worlds of Avium that shipped last year that we did updates for resolution scaling, frame generation, and other updates through this year. And then Arc Survival Ascended, which we haven't officially announced until right now. So we're doing that work also with the Studio Wildcard team. So we get an announcement at Unreal Fest. So let's talk about Project Legend. Project Legend is an internal R&D framework. It is not academic. It is building productized solutions for the work that we do. And that can be for our co-development, our ports, our side-by-side development, and our own internal original properties, and our remasters and remakes. So we're going to talk about the IHV integrations as part of this, but we're also going to hit profiling optimization, rendering, technical art, best practices. The project that we have with Legend, we're a very technology agnostic studio, but we're heavily involved in working with Unreal Engine. And on the Unreal Engine side, our Legend project, we do constant work in 4.2.7, 5.1, 2, 3, and 4, and latest. So what that lets us do is it lets us build solutions that the studio owns, and then we can take those solutions when we go to a partner and say, hey, we want to implement this for your game. And it makes a faster path for implementation. It's a more feature-rich and robust and tested solution, and it maintains ownership for us as a studio in our technology that we leverage for our partners. So as far as Legend goes, so very significant focus on UE. But Kevin, why don't you go ahead and talk about the resolution scaling side of things?
Yeah, so like we discussed, we have two backends for FSR. So we did quite a bit for the RHI backend support and the native backend support. And our key is to provide the software for all platforms, and we're getting there. We have 3 platforms right now. XeSS and DLSS are also part of our tech stack because we have to test everything. And you saw the testing grid.
All about the testing.
Yeah, we did a little bit of parity checks in our timings and how we compare against PC implementation. So we have some timings from PS5, depending on the different back buffer sizes and the actual scale primary percentage. Our tests here involve both 3.1 and when we did our old projects, it was 3.04, so we have some timings from them too. So this also shows TSR and 3.10. And one of the reasons that the previous slide didn't have some of the timings there is because, actually this slide didn't have some of the things there is because decoupling was not a thing with AMD 3.04. So we did what is possible, and then in 3.1, we actually did the decoupled timings as well.
Right. Awesome. Thank you.
You bet.
So another case study, Immortals of Avium, is a title from Ascendant Studios published by EA Originals. And that was an exciting project for us to work on. We came in initially to do optimization and performance help in UE5 best practices as teams were transitioning from UE4 to UE5 and really leveraging everything UE5 related. But as part of that, I really wanted to do what we could to improve the game. One of the things that is unique about us as a studio, as Enduring Games, is we tend to look at the partnerships we have and the relationships and say, okay, how do we make this, how do we bring this to our other partners and do something really cool for them? So bringing in DLSS and FSR were things that Enduring Games did. We championed this, we moved it forward, and we weren't satisfied with just doing PC. So we also moved that technology over to console for the first time and added frame generation and resolution scaling in Unreal Engine by way of FSR. And then we did a lot of work back and forth for having DLSS and FSR work well together. And some of that was branding and UX related. Some of it was very, very in the weeds technical related. So we could create a good experience for those folks. So we'll hit a few of those areas. But real quick, again, that was with Ascendant Studios. They were our partner on this, and they've just wonderful humans. And as they've moved on to their next phase with Absurd Ventures, and Absurd Marin, their new studio, we still stay in touch with those folks because it's the game industry, and we plan to always do great things for really great people. So we were aiming at PC, PS5, and Xbox series. The game shipped on Unreal Engine 5.1.1. And we integrated multiple solutions. Kevin, you want to go ahead and jump in?
Yeah. So we started with FSR, actually. We started with 2.2 specifically, and that's when we started discussions with AMD as well for later stuff. So we got to experiment a lot with the early releases and helped quite a bit with just getting in the tech and learning what's going on and what's the new things that's coming up, right? And then we also did NVIDIA DLSS and the full technology stack associated with it. But like I discussed before, there's swap chain hooks coming in. You're not just dealing with one technology anymore. We had to do a lot to actually support switching between frame generation technologies, and it's not just a out-of-the-box solution. And one of the things about this project was that we were adding resolution scaling and frame generation pretty much at the end. So we had to make a lot of product decisions with our partners and just internally looking at stuff. And there was a lot of trade-offs and what can be shipped versus not decisions going on. And as far as some of the challenges we faced, it's the first shipped version of FSR 3 on console. And we use native backends for both of them, so you saw the spoiler alert. 3.0x has only support for UI extraction mode. In the UE plugin, FSR provides a approach for UI where it uses the previous frame and the non-UI frame to actually extract the UI out and paste it into the new frame. And slate redraw is the other method they have when you use RHI backend, where it basically tells slate to draw again. When you use the native backend, you don't get this in 304. It is available in 3.1, but in 304 we didn't have that facility, so we had to stick with what we had, and there were some problems related to this specific aspect, and we'll see one of those things today. Because we are adding resolution scaling at the end, there were a lot of post-process materials that required support for screen percentage changes. Epic has some documentation with regards to view size and how to compute the new UVs. Very important that you set up full screen effects based on those guidances. One of the things we saw is a lot of the UI markers in world can have different behavior depending on what you're doing with slate. I will say this will be a constant thing I will keep saying, motion vectors. Motion vectors is the most important thing for any kind of resolution scaling to work, especially if it's temporal, and becomes a very key aspect of what you need to even drive frame generation as well. And two subtopics within that, we'll deal with some of the tech art considerations on that later. When you're dealing with full screen menus, you tend to have a choice between turning off frame gen versus not. Depending on what you need for the game, you might be disabling frame gen, and when you're doing that, it could have synchronization issues when you're doing those transitions. And one thing to note is, yes, there's a lot of reduction on what you're trying to get out of render target sizes and general render pipeline GPU times. But understand that frame generation also needs a lot of intermediate data and render targets to actually work. So it's not a free of cost. It's actually a significant enough cost to either make it a go or no go for your game. Secondary upscaling is something that Epic supports on Unreal Engine. It's a spatial upscaler that's run after the post-processing stack and then UI is overlaid on top. But that can help drive some of the memory footprint down or even give you some GPU perf back. Again, all of this is dependent on what your product goals are and product decisions around. So some of the, like I was talking about the slate redraw, there are translucent UI things that you have to consider when you are making the decisions on how your HUD is going to be in the game. This is one of the common things you will see. So on the AMD side, since it's a software approach, it is trying to calculate the pixels, and when it actually does the when it does the UI extraction method, you're going to run into that sort of stair-stepping thing on the UI. And in this case, we had to trade this off for another problem, and we picked this over that. One of the other issues we saw is with regards to a shield effect in the game. It's basically a thing that follows the player and uses the player's movement to move it. And when you don't have enough motion vectors to support it, and there's a lot of movement in it, you can run into issues depending on how the motion vectors actually get used. We worked a ton with AMD to reduce this problem over time, but understand that and this results from frame generation, not the resolution scaling part. So there's a lot of evolving tech here, and these are some of the problems you may run into. One other big effect that we ran into on Immortals was the sigil. So the player has a sigil on their hand, which is in the frame, and there's a lot of WPO and vertex animation-based effects on the sigil. And how that looks is basically it's doing a lot of those motions, and it's using the data, but there's not enough motion vectors the same way. Wow, I'm saying motion vectors a lot. To support that kind of movement. And we worked with our game teams to reduce this effect quite a bit, but again, there's a lot of trade-offs with amount of time spent with how much are you ready to ship with as well. Some of the challenges we faced with NVIDIA's DLSS is, again, a lot of the motion vectors we were able to solve on the DLSS side, and DLSS at that time was still released and a little more mature than FSR 3. We were still using pre-public FSR 3 to start and ship the game. But even with DLSS, we had seen the same problems in terms of menus and post-process materials not being up to date. One of the synchronization issues we had initially run into was Alt-Tab related, and when you exit the screen, the swap chains weren't getting torn down properly, and that was causing a crash, which was fixed over time from patches from NVIDIA. And like I was saying, because it has to deal with swap chain creation, there's that support we had to build for actually switching frame generation technologies. But yeah.
Cool. So all right, cool. Hot off the presses. So we're doing resolution scaling and frame generation in Arc Survival Ascended, and that includes console. So you all get to hear it first here. We'll do something official later, but this is official. It's recorded. No takebacks. So we're gonna talk a little bit about the IHV integrations. We're gonna talk about some of those impacts to the profiling and some more best practices. But this is a really good example of the evolution of the tech, the evolution of our implementation of the tech, and the opportunity to help another partner by way of our partnerships with the IHVs. The Studio Wildcard folks are really great. They go 1,000,000 miles an hour. And they had seen what the evolution of Immortals of Avium, both with the initial implementation, the updated implementations, and then some of the other perf and related things that we did. So they approached us and said, "Hey, we want you to do the same thing, just faster." So we said, "Okay." They're great. So again, Studio Wildcard, they're our partner on this project. We are doing PC, PS5, and Xbox Series. And then some solutions were already integrated. So there's a combination of us updating those or doing the interplay between the existing solutions and the new solutions. So we did AMD FSR 3.1 for PC, PS5, and Series. And we also support switching UI mode. Kevin?
Yeah. So like I was saying, 3.1 actually lets you switch between slate extraction versus our full slate redraw. Both of those have their own issues, and you have to deal with the issues as a fall-off. Slate redraw means you can't do async compute because slate needs to run on and you need to synchronize the calls to actually make slate render. We started with an RHI-only implementation to get it out first, and we were working on the native backend for the new engine version and the updated 3.1 interplay as well. VSync off was a important thing that Studio Wildcard really needed. So RHI backend wasn't going to be the final solve, and native backend was a very important thing for them because presentation is important. Waiting for presentations is very important for the non-VRR cases to reduce tearing as much as we can. Some of the things that we faced is the Unreal plugin for FSR 3.1.0 actually does not have the support for decoupling, resolution scaling, and frame gen. So this is the change you will potentially need to decouple that. The internal tech actually supports it. So you will be able to do DLSS and TSR with FSR frame generation with that change.
Yep,
right
and 3.1.1 released this week. So there are some updates and some changes that are a little bit of a delta from some of the things you're seeing here. So some things will be taken care of for you or updated slightly.
And 3.1.1 also has this fix. So if you're getting the new hot off the press stuff, we do have support for decoupling in the Unreal Engine plugin as well. Some of the things that was specific to Arc was they had a lot of UI. There's a lot of HUD. Some of the parts of the slate used to flicker, and we had to find what's going on. And part of this is, a lot of trying to solve issues that come up from resulting from resolution scaling or frame generation. You've got to work with the game team. There's no solo act here. It's not a It's just not going to happen. You need context from the game, and once you get in, you're not going to get immediate context, and you're not going to become the game expert. So we partnered a lot with our folks, with the folks at Wildcard, and we were able to solve this real quick. One of the things they have is a lot of emissives in the field, and FSR's auto exposure helped quite a bit to help with the res scaling part of this. Transparent UI is, again, a topic that came up because we're using slate redraw in this case, so we didn't run into those transparent UI modes issues. One thing they do have is because you're able to change UI mode from 0 to 1 for redraw versus native or extraction, tick for slate behavior can actually be modified. So AMD actually introduced a new CVAR for controlling whether the interpolated frame gets actual delta versus 0 for delta time. And depending on what you're trying to achieve, this can help in different ways. Again, memory overhead is a big thing. Arc is a open world, a lot of dinosaurs, and a lot of foliage. So memory is a pretty big thing that we had to work with the game team quite a bit, and we were able to fit FSR and make it happen. And we ran into a lot of hard to reproduce synchronization issues. And all you're going to get from GPU crashes is a box that looks like that, especially with shipping builds. We had to, and there were a lot of shipping only and dev only issues we had to take care of as well. There were some issues we fixed with the render target initializations on the FSR plugin side as well to make sure the correct MIPS were actually getting cleared. So that was a fun ride with Arc.
I've made a mini career out of dinosaur games, I just realized. We're going to do challenges and considerations. We're going to go through these pretty quick because I want to leave some time for Q&A. Just like real quick, do people have questions?
Oh.
Yeah, we got, all right, so we'll leave time for Q&A. Good. All right. So we'll go through this real quick. Okay, so yeah, every game has unique needs. This is a very big thing as you're working on your game, partners' games, work with samples and things like that. It really is not a one-size-fits-all. The stuff we make is all unique and amazing as an industry. And so it's not just a drop-in solution, and there is implementation work and product decisions and work that need to be done. Kevin?
Yeah. You're introducing additional workloads, right? GPU is not just throwing this trivially and saying, this is done now. There's a lot of compute work happening, a lot of graphics queue work happening, which means this can potentially push your existing game's workload and probably expose synchronization issues that may already exist and just not found or just caved away somehow. A lot of this, to debug a lot of the GPU crashes, you want to integrate tools and keep your game compatible with things like GPU breadcrumbs or Dread and capture tools and markers. One thing that we found so far across our 3 different case studies is that giving QA the CVARs needed for or responsible for the scaling and frame generation tends to help quite a bit when you're trying to triage a bunch of this. QA can hammer at it and give us all the data that we need. And one of the things that biggest takeaways from us is we worked a lot with NVIDIA, AMD, and to help raise issues and try to see what game-specific changes we might need for plugins. But understand that they may not be able to help you with console-only issues. And for resolution scaling, one of the things we mentioned quite a bit is motion vectors. It is very vital to reduce artifacts. You need at least FP16 precision to do motion vectors so that it's actually going to reduce the artifacts. All the materials may have output velocity for translucency, and WPO has some special case where if it's static, you might have to enable another flag in the project settings, which I'll talk about soon. For resolution scaling, intermediate render target memory footprint just for the scaling aspects is also a consideration. It's not free. One of the things we hope you take away from this is plan ahead. Like console support is hard. Memory footprint on consoles is also a hard problem. So as far as the best case scenario is the fact if you can start with scaling and frame gen on and do the entire development on it, but that's an ideal that nobody has the bandwidth for. So we'll take the best early approach as we can get. Or plan for secondary upscaling. That might be one of the ways you fit on console. And for frame generation, same way. One of the things that IHVs always recommend is try to keep your game optimized at 60 FPS. And as we talked about this before, this is about frame smoothing and not necessarily just doubling your frame rate. And the best case scenario is going to be 60 FPS, but anything under 30 can have a lot of artifacts because the interpolated frame is visible for a much longer time on screen. Input latency is a huge thing. UX is kind of a big thing for games, apparently. Try to do a lot of tests with those and see what works and what doesn't work for you. Motion vectors, again, for frame generation is also very important to actually interpolate the frame. One thing we found is full screen menus, since there's a lot of things that's happening without motion vector support, you're going to run into issues. And we found that it could just be better not running frame gen in those workloads. And UI can be tricky. You can have different cases that have different needs. Switching solutions is not just something that works. There might be edits to the plugins or the game that to actually support the problems.
So we'll spin really quick through some assets and technical art considerations so we can have some time for questions.
Mm-hmm. Again, motion vectors, motion vectors, motion vectors. You say it enough times, it should just work, right? Well, caveats. For WPO and static mobility, Unreal has this flag where you can output velocities for vertex deformation. If you have this on, it will actually output velocity vectors for those foliage things that are static but tend to move. The other case that you'll have to account for is pixel animation. Pixel animation cannot output motion vectors. Motion vectors is more of a vertex shader driven option. And pixel animation tends to circumvent that. So different technologies have a way of doing masks based on checkboxes and shading models, which directly drive a mask. And it will just turn away the temporal history and use the current frame instead. And for engineering, like I said, debugging is hard. GPU debugging, especially if the amount of options available in Unreal is great, but not every GPU workload will just work. Over time, you will tend to break some of this, but try to keep as much of these options compatible so that debugging becomes easier later. One thing that will fight a lot is when you're changing upscalers, please make sure that there's only one active at the time, especially when the UI change is happening. UI settings implementation is thus not trivial. It takes a lot of time to test, but it's important to take the time to test it as well. Yeah, and do a lot of the load time settings as startup cases as well.
Awesome, thank you. Yeah, so one thing that's really important is taking care of partners and gamers, right? When you look at AMD, Intel, NVIDIA, Epic, people have invested a lot in their brand, their technology, and they have guidelines, and they can help, and they want to help. And there is a combination of them wanting to prioritize and maximize their implementation, but they also want to play nice with other implementations because that takes care of gamers, which is who we're making all this stuff for. Gamers invest a lot in their gaming rigs, almost religiously so. So supporting their technology choices is really important also. So giving those options for different solutions really broadens the base that will play your game and feel taken care of, which really equates to brand loyalty and sales. Creating the broadest set of choices lets users pick the solution that makes them happy. That is different than the right solution. We want to make them happy, and giving them that choice lets them have ownership and agency over their local experience. Most consumers, consumer influencers and gamers are not professional developers. They don't understand the implementation work or technical details, and they'll make statements that drive me mad sometimes, but they shouldn't need to. And so I recommend not getting too hung up on it, as my staff tells me. daily. Special thanks. All right, it's dangerous to go alone. It's not just me and Kevin. We've got several folks at Enduring that have been key to what we've done for resolution scaling, frame generation, iterative implementation, tests, timings, everything. And then we have great partners at AMD, Intel, NVIDIA. The Ascendant folks, that was kind of our vehicle external to Legend, where we were able to implement these technologies and console for the first time. And Studio Wildcard is hot off the presses, as we keep saying. But they've been fantastic, and they've been really good about working with us as we help them see, okay, this is a game side thing, not a resolution scaling or a frame rate thing. But at the end of the day, we got to make sure the game is okay. And then Epic, we have a long history across multiple programs, and a lot of those things lent themselves to the success of these case studies and being able to do something for their engine that's not just what is in their engine. So I really appreciate that. All right, so there's some resources there. Those are all the direct links from the independent hardware vendors' sites. So pretty easy to get to, even if you don't have this slide. But really, we really appreciate y'all. Thank you for doing this. We've got a little bit of time for questions. So if you can pop up and ask those, that would be great. Thank y'all.
Thank you.